course, I thank the organizers for the invitation to be here. Really great pleasure to be in this conference because Nagaraj was one person where we could boldly go and discuss mathematics without fear of being judged. One of those rare qualities which you don't find it so easily, of course. And he is also a person, when we were students, he was staying at the Panini and he used to make dosas on every Sunday. And we were desperate to get an invitation to go and have dosas. Of course, we didn't. But then there was no invitation coming. So finally,
You said, of course, we didn't.
No, we didn't. We all wanted to go there, and this thing. Many of us were good friends with him. But there was Anil Maheshwari who found the trick of how to get an invitation. Is to simply say to Nagaraj, "Nagaraj, I'm coming," and Nagaraj will never say no. So we decided that after that we'll say Nagaraj. So then he knew, and then he said, "You come this week. The next person come this week." So we got our dosas, and that was very nice. Thanks. Okay, so again, apologies for this talk. This is the third time I'm giving. The first time I gave it, I think it was a bit too presumptuous because later found that the main theorem was completely wrong proof. Second time we got the proof of the main theorem, and this time I think there's one more addition, which is what we call the non-effective case. Also, we can do it. What are all the automorphisms? So let me start off. So I'm going to look at an elliptic surface. So the theorem as such makes bigger than this. Okay, it looks very clear. So the main theorem is K will be a field which is finitely generated over its field finitely generated over its prime field. One can also, or it can also take characteristic of K equal to 0. So that is or. And the reason I'm saying is at some point of time one makes use of the conjectures of Tate. So the theorems are valid in this context. And also I'm in mind whether to generalize it to higher genus fibrations. I don't know about that. But so in case any trouble comes, then one tries to restrict to fields which are finally generated over its prime field. So we have an elliptic surface. So for an elliptic surface E, so what we are having is C is a smooth projective curve. Curve over K. Is this okay? Yeah. And so we have a fibration X to C. So basically an elliptic surface is something which is given by an elliptic curve over the function field. So the generic fiber is an elliptic curve C over the function, E over the function field Kc. And the elliptic surface is, I will not write down, it's a relatively minimal, it's a regular surface, which is a kind of completion of this generic fiber. It's a relatively minimal. X to C is relatively minimal. There are no minus curves of self-intersection, rational curves of self-intersection -1 along the fibers, relatively minimal. And X is regular, it's a regular, and of course it's proper over C. Okay, almost all genus, all the fibers are of genus 1, the smooth reduction. So I'll also assume the following. Wait. I'm just assuming various other things on the surface. Yeah. So as Kapil says, it has a section. Pi has a section. which is the zero section. Yeah, so I should, because only then I can say it's an elliptic surface, otherwise I would have said curves of genus 1. And so that is one. Main thing I'm going to assume is that this fibration is semi-stable. So in other words, the singular fibers, or what are called the Codera type 1n, which is a bunch of P1s with rational lines. Each one of them has self-intersections, -2, and they intersect each other with this. So I'll take points maybe V0, V1, V2, and so on, Vn minus 1. So the number of components is n. So we have Vi squared, so -2, and Vi plus 1 is equal to 1. So the indexing set is Z mod nz. No rational curves of self-intersection -1 along the fibers. Okay, then it's one knows the thing that it's kind of unique. Okay, is there any other assumption I have to make? Yeah, I also assume that there is a rational point C, so that the class of the fiber is defined. Okay, C as a rational point. Ck is non-empty. Okay, these are the assumptions. So the next thing is what I want to look at is the Néron-Severi group. So X bar will denote, of course, X cross over K bar. Okay, and so the Néron-Severi group of X bar is the divisors mod algebraic equivalence. So if I want to define what is the Néron-Severi group of X, of course I would say divisors mod algebraic equivalence over K bar. So this is the image of, if you want, the Picard group. Pic of X inside in S6. Yeah. Yeah, but yeah, singular fibers are need not be defined.
You assume many singular fibers?
Many singular fibers, of course.
But all of them are.
No, huh?
All of them are type.
Yeah. No. The n will change with the fiber. Yeah, of course. Yeah. Yeah, wait. You have got me this thing on rationality of the singular points. Okay. Yeah, so see, there are points at which the. Yeah, no, the. Okay. Wait. Yeah. Right, sorry. I assume that all the singular fibers are rational. Okay. It's geometry. Yeah, right. Yeah, absolutely. I assume. Yeah. No. I do make the assumption. All the singular fibers are rational. Okay. All singular fibers are defined. Okay. Or defined. Okay. And in fact, rational over K. The components are also rational over K. Okay, what is called split multiplicative reduction. Okay, this is what is called, in the elliptical language, it's called split multiplicative reduction. Yeah, so this is the. Okay. Oh, sorry? Yeah, I'm assuming they are rational. Yeah, that's what. I'm assuming it's split multiplicative reduction. What is?
This question is points of C corresponding to singular.
Yeah, they are rational.
They are also rational.
Rational.
So that's all contained in this. They are rational and the components are also defined over the same.
Same this thing. No, the components will be what is called split multiplicative reduction, which is what this thing. So I'm, yeah.
So you don't have to say separately C cannot. The images will give.
Right. Yeah. No, I've forgotten one more thing. I have to say that the elliptic surface is potentially not isotrivial, which amounts to saying that the J invariant is not algebraic over K. Semi-stable is potentially non-trivial. Absolutely. Sorry. Yeah. Okay.
There's a non-singular fiber.
Yeah, there is a non-singular fiber. There is a non-singular fiber. It's a semi-stable thing. I can also assume for the theorem, I assume all the components are greater than or equal to 3. Semi-stable in the sense of semi-stable. There are at least 3 components in each fiber. It's not strictly needed, but anyway, it's for one of the theorems to make this thing, it's cleaner. Okay, so that's second thing is the reason why we need semi-stable is the following, which got also clarified after some discussions with Nagaraj long back, is that I have to consider base changes B to C, and you have this curve here, X, and you can take the base change surface, which is basically, you look at X cross B over C. Yeah, so I have to be a bit careful. The curve B might be defined over L, maybe defined over L a finite extension of all separable extension of K. And so basically I would base change to C cross L over K in order to define the base change. So let me say C comma L. And you take, so this may not be relatively minimal and regular or whatnot. So you have to take the relatively minimal regular class of that, which I will call that XB. So XB is the relatively minimal regular thing. Okay, so there is some relationship between XB and this thing. The point is that when X is semi-stable, and then you form this, so then there is a map here. So this exists for semi-stable. This map. Okay, so it's a generically finite map. Okay, so that map exists for, and so what you can talk about is, so via this you have a map from.
What is the relationship between that X at the top and the fiber product?
See, the relationship in this case, it's a blow up when X is semi-stable, but when X is not semi-stable, XB, this is a blow up. And this has a map, so this map is there. Okay, in the case when X is not semi-stable, see when it has what is called potentially good reduction, then you don't have a map like this. You might have to blow down the singularities and blow up. So that, but in the case of semi-stable, it's a blow up and then it's this. Yeah. And so you get a map. Okay, in this case. So that's the reason you need to work with semi-stable. Otherwise, the hypothesis doesn't make sense. So then, so you have a map from the Néron-Severi group of X to the Néron-Severi group of the base change of XB. No, you can pull up, and it will satisfy that. So the Néron-Severi being on a surface, you have an intersection product, and so if I look at, so I'll denote on the devices the intersection product by this thing. So B star is degree B times the inner product XY. Okay, so you get these things for satisfied.
These are all preserved under that fact split multiplicative blah blah.
Yeah, everything is. Split multiplicative, yeah, that's the other usage of the term stable is that everything is kind of stable under all kinds of things. So, yeah. Of course, every elliptic surface has a potentially semi-stable reduction. So after a base change, all elliptic surfaces which are not potentially isotrivial will be semi-stable in this sense. Okay, so that is. Yeah, is this okay? So I'm going to define a universal Néron-Severi group. So universal Néron-Severi is to, so I look at the NSXB with the intersection pairing for all base changes B from B to C, where this ranges over all the finite separable covers of C. Okay, so that's a. Okay, so this is my universal Néron-Severi. So maybe I don't know whether I'll maybe say it as n of x. So I should say it's a collection of all such. And they have pullback maps, and with the B star from. So I should say if I have map from there's a B to C, and there's a map from A to B. This is A, B. So you have pullback map A upper star from NSXB to NSXB composite thing. And all these things are compatible with whatever sense. Okay, so I can define, so you can define morphisms of universal Néron-Severi group. Okay, so the universal name is for that is that I'm considering all base changes, so you call it universal in that sense. Okay, so so that is the thing, and I would say a morphism is said to be effective if for each B, so I'm okay. So this is between two. So morphism of two this thing. So I have x to C and another curve x dash to C. So I'm giving a morphism from nx, universal Néron-Severi, to n of x dash, and which means for each B, you have a map phi B from nsx of B to Néron-Severi of x dash of B, the base changes. And if for each B, this map phi B is effective in the sense it sends effective cone to effective, the cone of effective devices to effective devices. Okay, so these are the definitions.
You have a bunch of maps compatible with these pullbacks.
Yeah, I have to say it's all compatible with the pullbacks. Yes, of course. Yeah, that's what. I have not said this thing, but you put in the usual assumptions. It should be compatible with all these pullbacks and structures. Yeah, that's I'm not going to write it down. Yeah, it's clear, right? What should be a morphism of. And it's compatible, of course, with the intersection pairing. Okay, so the first theorem is that, of course, it's compatible with the intersection pairing. The intersection pairing is non-degenerate, so every morphism will be an isomorphism if it exists. So morphisms means these are basically isomorphisms of universal this thing. So I'll call this map capital Phi. So if there is a morphism, if there exists a morphism, an isomorphism, maybe let me say isomorphism, phi of the universal Néron-Severi groups, then X is isomorphic to X dash over C. Then there exists an isomorphism. Okay? So I should say that. No, wait. I'm just. So that's one. So the effective version is that if it is effective, plus effective implies that the map phi comes from a isomorphism, from an isomorphism X to X dash over C. Yeah, so effective means the cone of effective devices goes to the cone of effective devices. That's, yeah. So I should recall, first of all, the usual Torelli theorem for elliptic surfaces is known to be false. Whenever there is a family of elliptic surfaces, a non-trivial family,
Without assuming effectiveness, you get that any abstract morphism is given by an actual.
it's an isomorphism, yeah, right. I'll come later. I have a full classification of what are all. Oh, sorry. No, please, yeah, no. Yeah, I'm just saying that there is an isomorphism, but the map phi on the Néron-Severi may not be induced by a map of geometric map of surfaces.
You seem to say if there's an isomorphism, then it's induced by a map of.
I'm not saying that is only in the effective case it's induced. Phi comes from an isomorphism.
You can have non-effective reflections.
Yes. That's exactly what is this.
So so if there is an isomorphism, there is a map, but that map may not have anything to do with the isomorphism.
Yeah.
That's the first part.
That's the first part. But wait, I'll clear the first part soon. I'll for a single surface X, I'll tell you what are all the automorphisms. I will tell you.
The map, the morphism of Néron-Severi groups is induced by a geometric map, then it has to be effective.
Right.
But so the point is that in the first part of your theorem, that map from X to X prime corresponding to phi.
I'm not saying corresponding to phi. I'm just saying then the surfaces are isomorphic.
So that's one. It doesn't correspond to phi.
It doesn't correspond to phi. But when it is effective, plus effective, so I should say plus effective, theorem 2 is theorem 1 plus effective, hypothesis of theorem 1 plus effective, implies that phi comes from a geometric map. So let me make the following.
Even to k equal to k bar, there is something here, right? Because that
No.
genuine curving.
Yeah, right. Yeah. Sorry? Yeah, when k equal to k bar, any field of characteristic 0, it still needs to be proved. Yeah. Right. But the point is, the reason why I'm, okay, see, I need to assume that the Néron-Severi groups are finitely generated. Yeah, right, okay, yeah. Anyway, that's fine, yeah. Yeah, under this hypothesis, the Néron-Severi groups are finitely generated and free. Yeah, but I'll assume to start with k is finally generated over C or its prime field because I'm going to use state conjectures. So so let us, okay. Yeah, so a couple of remarks. One is that Torelli fails for a single elliptic surface. In this sense, fails for elliptic surfaces. It's not too difficult, but let me not say. Basically, whenever there is a family of, say, for instance, the family of elliptic surfaces, say rational, non-trivial family. Such a the family of rational elliptic surfaces is 8-dimensional, and what happens is you can look at the generic fiber, and the Néron-Severi group will be isomorphic to the specializations for outside a Hilbertian set, whatever it is. So you will have, once you are over a field of infinite cardinality, you will have enough examples of elliptic surfaces, rational elliptic surfaces, for which the Torelli theorem fails, because for the rational elliptic surfaces, the relevant cohomology group, the second cohomology group will be just the Néron-Severi, and the first and the third will be 0, and others are the same. H2 will be given by the Néron-Severi. Okay, at least, yeah, if I'm working over this. Essentially, tensor whatever C or R or whatever, or QL. Okay, so that is one. The second thing is that right. Okay, so that's I had probably some other remarks in mind, but yeah, okay. I need to say the other important thing. Two is that there is a theorem of Torelli for K3 surfaces, where you look at the or complex numbers, and so you look at the second cohomology with the Hodge structure and the polarization, and if it has an intersection, whatever, the second cohomologies of X and Z, the integral Hodge cohomology, and then you look at the Hodge structure and look at the polarization, and if you know that they are isomorphic, then you will know that the surfaces are isomorphic. And further, what one can make sense of effectivity hypothesis, and it's a theorem of Piatetski, Shapiro, and Shafarevich, that if you further impose the effectivity hypothesis, then such a map is induced from an actual morphism of K3 surfaces. Okay, so basically the same thing works here, but you will have to consider all base changes. Okay, that's a thing which is there. Yeah, no, my starting point is state at some point. Yeah. I'll have to use states. Yeah, I think so. I think so. I'm just. As I said, just assume. Let's assume K is finally generated over its base field. Let us work with that, and that is over its prime field. Yeah. So it's an arithmetic field. K is finally generated over its prime field. So I'll come to it. I'm not. Suddenly I'm this. Yeah, what you and Parmu were asking. Yeah, so this is so it's a. Okay, so I'll take the effective isomorphisms, non-effective. So this is something new, which is I didn't have it last time I lectured. So what are the non-effective isomorphisms? So first of all, for a, if you have a vector v in any lattice, suppose if you have a lattice L and it has a vector v with self-intersection v squared equal to say -2, so then you have what is called the Picard-Lefschetz reflection. Reflection, which is you send an element to x is sent to x comma wait, S alpha is u plus, yeah. So let's take, so v squared is -2. If I take v is, this is -2, -2v plus v is -v. So this is a Picard-Lefschetz reflection SV. So SV has a thing that SV of v is -v, and SV restricted to v perp is identity on v perp. Okay, so it's a reflection around the plane orthogonal to this thing. So this works in full generality. And so what's happening is, as I said, if I take a singular fiber and an irreducible component, of x to c, the base curve, the base elliptic surface, irreducible component, say, so I have this any vi, I take an irreducible component of this. So we have this vi squared equal to -2. So you have the Picard-Lefschetz reflections SVI, which is only acting on the Néron-Severi of the base space. Okay, so the point is that so theorem or whatever it is that this Picard-Lefschetz of the base space, because it's an element of the Néron-Severi. It's a self-intersection -2, and any element which is ±2, you can always define a Picard-Lefschetz reflection, a wild reflection of a Picard-Lefschetz. Okay, and I'm saying so it makes sense automatically for the Néron-Severi of x, but it can be lifted to a universal isometry.
What we call the base space.
X to c is a base space. I fixed x to c is the base elliptic surface. By base meaning I'm saying I'm Néron-Severi of x, but I'm just saying these Picard-Lefschetz isometries can be extended or lifted, can be lifted to universal isometries. Okay, so of course by construction they are non-effective because it sends your divisor v to -v. Okay, but these are, and so can be lifted to universal isometries. So maybe I'll just say A.
This is the theorem because after pulling back,
You have to.
you don't have necessarily a corresponding gear.
Right, you have to check that. So you have to know where it pulls back. You have to give a map you have to lift it as a universal isometry. So I have to know where this V goes to. Okay. So the point is on the geometric space, if I pull back, first of all, I'll have to figure out how this, the singular, what is the map on the pullback map on the singular, on the irreducible components, and then automatically get this map. So I'll tell you what this map is in a moment. So right now. So what is this map? So the map is so let's. So before that, I'll say one more thing. This on NSX, whatever. Anyway, so you just fix a singular fiber of type 1n, and the Picard-Lefschetz isometries based on the singular fiber. Say this corresponds to some xs. Okay, this is a singular fiber, which is pi inverse of some point is. On the singular fiber, and it's of type 1n over S, they generate the affine while group of type A tilde. Okay, basically what this means is that they satisfy the following thing, that SVI squared is equal to identity, and SVI plus 1 cubed is identity, and SVJ is equal to SVI if Vj and Vi don't intersect. Vj and Vi don't intersect. Okay, this is very similar to the permutation group, except that this. Okay, I am using the cyclic notation for this. They are commute. The components don't intersect. If Vi and Vj, or rather I will say I minus j is greater than or equal to 2 in sum, whatever this. Now I have, if I am saying I take the reflection around this and this, then they will commute. But the reflections around this two things are like permutations which are one. Okay, so that is I want to describe the map on the singular fibers. So what happens is, suppose if I assume that it's totally ramified, which is an interesting case, that I have 1n and there is a ramification, locally ramification degree, total ramified of degree d, so then it becomes, one can check it's 1nd. This 1nd which will map to 1n basically, or rather. So this I am V naught Vi, and this will be W naught, where W naught is the component of the zero component, where the zero section is this. So this will be W naught W1 and Wnd minus 1. Okay, so I'll explain where this reflection goes to SVI. Now I want to say what the pullback map on the Picard-Lefschetz isometries is.
Back to not to the fiber product, but we go to the blow up.
Yeah. Blow up. Yeah, you take the fiber product and take the minimal, the blow up, the minimal regular model in that, in the birational. No, I'm saying if I've taken my elliptic surface, I pull back and do the blowing up to make it minimal, regular and whatnot, that singular fiber will be of type 1nd. over that point, assuming that the base map is ramified of degree d over that 5, right? So I have a 1n_d and maps to 1n.
Each node will become, after base change, will become a AT times singularity.
Yeah. And then I will have to desingularize that.
Also, generically, there will be something. Actually, we first normalize and then
Yeah, normalize and this. Right. Yeah. Anyway, in IIT Kanpur language, my fundas are goal in that, but I don't want to say more. Okay. But so you have this fibers W0, W1 and things like that. You have to figure out where these vectors move back under the pullback map that is there, but let me say where the Picard reflections go to. It's pretty neat there. So what you do, so I want to say where V0 goes to. The SV0 goes to. Okay, so what you do is look at chains of vectors. Say suppose if I look at a chain, say Wi plus 1 plus W, say J. Okay? So one can check that this vector's square will be -2. Okay? And also, right. So this is a chain, say, based on some interval I comma j. So let's call this SWIJ, right? Now, sorry, this is the vector is Wij, and these vectors are orthogonal. Such vectors are orthogonal. These vectors are orthogonal. Unless, let me just say, if the supports anyway, let me not say what this is, what the problem. It will soon this thing. So where does V0 go to? So the SV0 goes to product of S, W, I. So I will say the intervals of length D. So I plus D. If I had Wi and Wi plus 1, it's D minus 1, right? Where 0 is in this interval. So you take the product of all such intervals. Okay, so that means it's based on reflections. So these reflections commute with each other. So these reflections, if they have non-empty intersection, if the interval, so let me call this interval, such intervals of length d, I'm fixing the length is d, there are only d vectors involved, and if this intervals I intersection I dash is non-empty, then SWI and SWI dash commute. Okay, so it's basically, I'm just saying it's a product of intervals of length of I is d and 0 is in the interval. Okay, length of the interval is d. The number of vectors, whatever is the definition, the number of vectors involved is d. Okay,
Because all of them contain zeros, they all commute.
they will all commute. Okay, so for instance, if I am taking, degree 2 and V0, SV0 will go to the reflection based on SW minus 1 plus W0 times W0 plus W1. That's it. It's the product of two reflections. Length 2, yeah, right. Okay. So they will all commute, and one can check that this. So this is the definition for SV naught. Where does SVI go to? SVI goes to a similar thing, but based on DI. So it's based at D times I. Instead of 0, it's based at DI. Instead of 0. See this V1, you will have to look at the dth vector, and all the elements will contain, all these intervals will contain SWD. D will be there. And V2 will have 2D and things like that. Okay, so that's a yeah, so this is the lift. So what happens is that this collection, okay, so I've described what, so this collection makes up the universal isometry corresponding to the base one, and this gives you a representation. This defines a representation of the affine Weil group W of an tilde, sorry, I should have said it's minus 1 to Weil group, affine Weil group of in D minus 1. This is a homomorphism, which is closed under this thing. If I take a further one, W of A tilde NED minus 1, whatever, all these things are coming out. Because that's this thing. Okay, so of course I have to say that these reflections, I have not said it, part of the picture is to say that each of these reflections are in the affine Weil group. They are generated by the base reflections. So I can define these maps again. Okay, so then the theorem is to say that apart from the, there is a trivial automorphism, which is every vector goes to its minus vector. That's this thing. And then you have the effective automorphisms, one can say, they will be given by translations, by sections. And another thing is the automorphism of the generic fiber, the inverse map on the generic fiber. That is, the generic fiber will not have CM, that is a general, it will have only one automorphism. And then apart from that, you have the product of the affine Weil groups based on the singular fibers. So they will be the automorphism group. Okay, so I don't know, I have around 10 minutes. So let me say what so is that okay? I think that's so this is classifies fully the effective, the non-effective automorphisms also are given. The universal non-effective, universal automorphism group is fully determined. See, apart from the effective automorphisms, which are easy to give because they are geometric, so then I'm just saying that this is. Okay, so, yeah. No, the affine Weil group semi-direct product with the effective automorphism group, which are geometric.
The surface automorphisms combined with the affine Weil group is the full.
And the minus, that's it. Yeah, surface automorphisms, which is this.
You talk about the affine Weil group, that means there's only one point.
No, for every singular fiber of the base curve of the base surface, you take the affine Weil group based on all the singular fibers of the base surface. They'll give you all the automorphisms. So there are no further automorphisms. That is the thing. Okay, so that is a so let me see what's the schema of the proof. Oh. Okay, so let's give an outline of the proof. So the step 1 is to say fiber goes to fiber. Fiber pulls back to fiber. Fiber goes to fiber. So recall I have a map of the Néron-Severi of the universal morphism of to this thing, and I have a class of fiber. I need to say that the class of the fiber goes to class of the fiber, plus minus fiber. Okay, and so the reason is as follows. What happens is I have the zero section and I have the fiber, and so they form a unimodular pair. So the space generated by the zero section and the fiber take the subspace ZO plus ZF. So what happens is this forms a, one can check it's unimodular. Okay, and basically what you use is you use a divisibility property. See, if I have map of, say I have X and I have sorry, this is C and I have B to C. So if it has degree D, then D apostar of F is F of the D times FB. Sorry, B apostar. The degree of B is D. This is B and degree of B is D. So the point is that the fiber, the pullback of the fiber is a highly divisible, is divisible by D, where D is a degree, and you write this because you know that the Hodge index theorem is true. You can this is unimodular. The surface is the thing, so you can write this plus orthogonal complement. Right? Yeah, as I said, this is a unimodular space, but the zero section pulls back to the zero section, so that cannot be divisible by D for all this thing. So if you have a fiber, it goes to the fiber in the base, if it goes to A times O plus B times F plus some divisor D, which is orthogonal to O and F, then when you pull back by sufficiently by D, this under pullback, this goes to when you pull back under sorry, this is should say constant C, and the B upper star, this pulls back to A times O of the section D plus whatever this is C times DF plus this is some pullback of B upper star of D. Right? But this should go into whatever it is on the other side. The fact that it's divisible by D will imply that this is equal to 0. And then you use orthogonality to conclude this. Okay, so clearly one uses base changes to prove this, the fiber goes to fiber. So once you have fiber goes to fiber, then with some calculation, step 2 is to say that the singular components, singular fibers are same or isomorphic. Or identical. Let me say or identical. That's not really needed, or let me just say that before that. Yeah, that one has to prove that. One has to prove that. What I'm saying is, yeah, so let me say that the subgroup generated by singular fibers goes to subgroup generated by singular fibers. And now what happens is we use the fact that the Néron-Severi of X, it maps to the model well group of X. And the kernel is 0 section plus a thing generated by singular fibers. What is called the trivial lattice. Yeah, so I'll have to say that the sections are mapped to sections. Some amount of work, but I can say that the trivial lattice is fixed. And so you get a map of model well group. So you'll get a map from model well group to model well group of X dash. And so in particular on torsion, and you use now you use state to conclude. So this is model well group of the generic fiber E. To conclude that E and E dash are isogenous. Okay, that still doesn't say that the surfaces are isomorphic, X and X dash. But what happens is one can go ahead and say that the singular fibers are identical. They are the same singularities and whatnot. Plus isogeny will imply that the surfaces are isomorphic. The reason is the singular fibers are at the same points over C, and they are of the same Codera neuron type. In that sense, it's the same. Yeah, the type of singular behavior is the same at the. Sorry?
But the base curve is the same.
Base curve is the same. It's about the same. See, you can change the pullbacks are at your hand. So you can, at one point, you can have a ramified pullback which is unramified over this thing. So the ramification behavior will immediately say that the amount of things has to be the same. Yeah, see, now if it is, if the singular type, I have this, so X to C, so if it is singular here and X dash to C is non-singular, I can pull it back by a highly ramified thing, and you will get very easily, you see that you can't have, such spaces sitting inside the Néron-Severi. That's not too difficult to see that, but it's not, once you know that the fiber goes to fiber, then some amount of calculation will tell you that the singular fibers are mapped to singular fibers. That once you do that, then it's fairly easy to say that the set of singularities are the same, and the reduction type is also the same at those singularities. So that's what I'm saying, singular fibers are identical. Identical meaning that they are the same in both the cases. Can be identified. It's okay. Yeah, but the problem is that, oh, sorry? No, you see, the base change B upper star sends it to I and D, and you can't I and D and I, see IE and I. Oh, sorry?
You're assuming everything at I and I.
The n changes with the base, right? If suppose the singularities are not at the same point, you can pull back at very highly ramified at one point, and then that singularity becomes I and D, and ND becomes much larger. So then you don't have an isomorphism from that to the other things. Once you know the singular fibers map to singular fibers. These spaces are all, they are orthogonal to each other. It gives you an orthogonal decomposition of the fibers of singular type. They are kind of, yeah, but see, the point is that the elliptic curve, E dash is isogenous, so it's E mod some torsion element T T is some torsion element. And what happens is, on the singular fiber, so if I have one n, if if this torsion fiber, this is for your x and x dash, if T runs, it's a torsion element, so if T runs over something, so this is component A, see torsion element. So then when I go model on isogeny, this one will have invariant 1 on Na, and if it goes out here, so T as order A, T to the power A equal to 1. Okay, and if it, you know that it's this component is GM, it will be defined, and if it goes out here, then the reduction will have type 1 Na. So once you know that the singular fibers are the same, what you will see is that you cannot have an isogeny unless the generic fibers are isomorphic. So this will imply that E is isomorphic to E dash, and which will imply that X is isomorphic to X dash over C. So the first theorem will be proved. I am already this thing, so it's, I think, sorry, I've given a proof of the first. The second theorem, there is a, see most of this thing, so what you do is now you assume that X is isomorphic to X dash, and then you can iterate this map phi. Okay, once you have proved the isomorphism, I can iterate this phi, so then I will work with phi squared and whatnot. And after this, the proof proceeds fairly along logical lines, except there is a trick to prove the effectivity theorem. There's some slight Galois descent, but luckily, yeah, it's not a difficult trick. But apart from that, the rest of the proof is, I would say, fairly logical. The first step is to show that X is isomorphic to X dash, and then that allows us to iterate the map. And then, so what the main thing is to say that if you have a map phi, which is identity on the singular fibers, and sends sections to sections, then this implies capital phi is identity. Okay, so this is what you have to say. Once you say this, then, and this is the only one which requires a bit of trick. But if you have a universal isometry which is identity on the singular fibers and this sends sections to sections, then it is identity. Yeah. Okay, so I'll stop here.